So, a couple of announcements. Actually, first of all, how was Thursday's lecture? Did you enjoy that? So Ryan, I think, covered non-parametric regression from a different point of view, right? Looking at it from splines and things like that. I think he talked a bit about trend filtering, which picks up inhomogeneous regression functions and is not a linear smoother. That's what typically to do non-homogeneous regression, where you have different amounts of smoothness in different parts of the space, you can't use linear smoothers. So I thought it was nice. I told Ryan he could talk about whatever he wanted to, but I kind of encouraged him to talk about that stuff because I thought it was a nice complement to what we had done. So what we want to do now is finish up linear classification, then we'll do some non-parametric classification, and then, contrary to what's on the schedule, I think we're going to do another bit of theoretical foundations. We'll talk about minimax theory, and we'll talk about how is it, because I keep mentioning minimax results. I finally want to show you the basic techniques for establishing how difficult is a statistical problem, which is really what minimax theory is all about. Before I do that, there was 2 requests on Piazza for delaying the midterm. So I thought we'd do this democratically, and those who show up on time get the vote. So you have all the power. Because the midterm is right now it's scheduled for shortly before spring break. But there was some request to do it after spring break. So I see a sharp no here. Yeah, I mean, to me, it's like, let's get it out of the way, would be the way I'd think about it. But I just thought this isn't a democracy, a classroom's a dictatorship. But we'll take a vote anyway, and just to get a sense of how people are feeling about it. So, didn't you know that? You didn't think a classroom was a democracy, did you? Yeah, I might. What I'm saying is the vote isn't binding. But I do want to have a vote to get a sense. So how many people would prefer to keep it where it is right now? Okay, how many people would prefer to delay it? That's what I was afraid of. It's not a clear decision. It's kind of split. So if it was clearly in favor of delaying it, I would have said let's delay it. But since it seems to be kind of split, I think let's just get it out of the way. It's not a big deal. We'll do a midterm. So we'll just do the midterm when it is scheduled. Someone asked if it could be take-home. You don't want it to be take-home. If it's a take-home exam, I'm going to have to make it way harder. So I do not think it's to your advantage to suffer over it. You suffer longer with a harder exam. I don't see any advantage to making a take-home exam. It's better just to come in, spend an hour and a half, get it out of the way, and forget about it. So that's the decision. All right, good. Well, when we get closer to the time, we can talk about what will be on it and so on. It's still pretty far away, right? Any other questions about or comments before I continue? Yes? Will there be a practice? We'll see. I haven't decided yet. Probably. Okay, any other questions? All right. So what we want to finish today is linear classification. And as I pointed out earlier, there's many different routes to getting a linear classifier. We talked about one, which is Gaussian discrimination. You take the distribution of x given y to be Gaussian. You find the Bayes rule, and it turns out to be a linear classifier, at least if the covariances are equal. Another way to get a linear classifier I'm not going to talk about is just to do a linear regression. Linear regression is kind of a funny thing to do because using this as a working model, y can only be 1 or 0. So this model could not literally be true. On the other hand, it doesn't mean you can't fit it, get a classifier, and sometimes it actually works pretty good. So this isn't what people normally do, but if you went through this, of course you would get a linear classifier. Another one that's in the notes I don't think is worth spending much time on is a slightly different approach called Fisher linear discriminant analysis. You can look at that if you want. What I want to go on to is logistic regression, which is probably one of the most common classifiers. You would have seen a bit of this, at least, in 701 and 715. So the idea, I'll remind you, is that we put down a working model that the probability of y equals 1 given x to be a parametric family, But instead of linear, we use this logistic function. The advantage being that this is always between 0 and 1, which makes sense for a probability. And that's the basic logistic regression model. It's a parametric assumption, so of course we're using it to generate a classifier. We're not necessarily assuming that this is the correct model. And so we'll call this pi. Actually, we'll call it pi of x beta. But now when you get a string of data, your data are Bernoullis, right? They're either ones or zeros. They're not IID because the distribution depends on x. They change with different x's. They're independent, but they're not identically distributed. But they're still Bernoullis. So you can still write down a likelihood function, which will just be the, I have two pi's here. This is the product pi. And then I have these guys, successes and failures. So successes, for a Bernoulli, the likelihood is the probability to the y, and for a failure, it's 1 minus y. So it's the usual Bernoulli likelihood function, except that now there's a covariate x in there, and there's this, implicitly, these depend on beta. And then this turns out to be a concave likelihood function, so you can find the MLE. And that's it. Now your classifier is a plug-in classifier, which is 1 or 0, depending on whether the estimated probability is bigger than a half or less than a half. This logistic function, though, the probability function is logistic. The classifier is linear. Why? Because if you just ask, when is this bigger than a half, you can just rearrange it and see that that corresponds to beta transpose x being bigger than something, right? Just by rearranging this term. So the dividing line between 1 and 0 is still linear. The probability function is not linear. The decision boundary is still linear. So logistic regression, it's a nonlinear regression estimator, but the classifier that comes from it is another linear classifier. It's another way to get a linear classifier. The way you actually find beta hat, people usually use Newton's method. And since I don't talk much about computation here, I won't go into the details, but they are in the notes that if you go through Newton's method, the steps have a very simple form. It looks like you're repeatedly doing weighted least squares. It looks like you're doing least squares with a set of weights, and you keep updating the weights. Okay, it's not so important for this class, but the steps are there in the box for you, page 17. It just turns out to be a case where the Newton's method leads to a very simple, interpretable set of iterations. The point is that since it's a concave likelihood function, finding the MLE is quite simple. So this is usually pretty fast. And so doing this classifier is pretty easy. We have a simple model. We get the likelihood. We can maximize the log likelihood using an iterative technique. You can't do it in closed form, but you get a simple iteration. And then the plug-in classifier that results is another linear boundary. And that's probably one of the most successful and simple classifiers out there. Before you try anything fancy, I would suggest doing logistic regression. Okay, and here's an example. Example 10 is this coronary risk factor study I mentioned earlier, where we're trying to classify people. Y is, I think, whether they had a heart attack or not. And then there's these features. One of the things that comes out is, since we have a parametric model, any software that computes this for you will also compute the Fisher information for you. And so we automatically get out standard errors and confidence intervals if you want. So what I'm showing you is a typical output from R, where I get the beta hats. So that's the quantities that go into the classifier. But also you get standard errors. There's a walled test for testing whether the coefficient is 0. There's a p-value and so on. So this should all be taken with a grain of salt, because those things are only meaningful to the degree that the model is approximately correct. The classifier is fine. It doesn't require the model to be correct. If it classifies well, it classifies well. If it doesn't, it doesn't. That it can classify well even if the model's wrong. The inferential statements are only valid to the degree that the model's correct, or at least approximately correct. But they are there. You get them sort of for free once you've converged to the MLE. Getting the Fisher information matrix numerically is very simple. And so you do have those inferences if you want them. So that's logistic regression. It's very simple. Any questions about logistic regression? Yeah.
Just a quick question about how to interpret these big values. Regardless of whether or not the model is the correct model, are these legitimate p-values for the linear independence of the?
No, what they're testing, you're testing the null hypothesis that beta j is 0 versus not 0, under the assumption that the logistic regression model is the correct generative model. And so they're only valid if the model is correct.
Usually we should solve the parameter beta from minimizing some loss function. But here we used to maximize the likelihood.
Yeah.
Are they the same?
Well, yeah, you can always view maximizing the likelihood as just take minus the log likelihood as the loss function.
Is that the loss function has some relationship with the training error?
Yes, it does. So getting a little bit ahead of ourselves, but if you think, again, remember I've drawn this thing before where you have a linear classifier, it's either wrong or right. And it turns out if you think of the logistic log likelihood minus that as a loss function, what you're doing is you're really approximating it with a function that looks like this. So another way to view logistic regression is it's a surrogate loss function for the 0-1 loss. And there's many other ones. We'll talk about that. The hinge function, the add-a-boost function, there's other surrogate loss functions. However, that's not usually the way people come up with logistic regression. They usually think of it as, I've got a parametric model for the probability function, and I'm just doing maximum likelihood. That's the usual route to logistic regression. Any other questions? Let me just repeat again how useful logistic regression is. A rumor I heard, and I can't verify whether this is true or false, is that when you do a search on Google, they have billions of dollars at stake about putting links there that they think you're going to click on or not. They're doing, my understanding, and I can't back this up, but is all they're doing is a gigantic logistic regression. They're just predicting, yes, 1 or 0, whether you'll click on this link or not, and it's just a huge logistic regression they're fitting. So I don't know that's for sure. It might just be a rumor. I think it's true. If it is, it just shows logistic regression can make you billions of dollars. Okay, that's a success story for logistic regression. They're actually doing sparse logistic regression, which I'm going to talk about in a few minutes. On the other hand, maybe they've given me misinformation so that their competitors will be misled or something. Who knows? I just want to mention something here about after doing Gaussian. If you think about the Gaussian linear discriminant model, that's saying x given y is Gaussian and y is Bernoulli. Logistic regression, we're saying that y given x has this logistic form. In fact, if you took the Gaussian linear discriminant model and computed what is the corresponding regression function, it would be a logistic function. You can derive the logistic regression by assuming the Gaussian linear discriminant model. The resulting, let me say that again, if I assume x given y is normal, and now I, by Bayes' theorem, compute the probability of y given x, the form of that will be a logistic regression, but you're not estimating the parameters the same way. One of them you're estimating the parameters of the normal directly. One of them you're just directly getting the conditional log likelihood of y given x. So what's the relationship between linear discriminant analysis and Gaussian and logistic regression? So the way to think about this is, if you think about the probability in general, In general, we have these random variables, x's and y's, and you just write down some arbitrary probability. And now imagine factorizing this. I can write this in two different ways. I can write this as the probability of x given y times the probability of y. But I could just as well have written it as the probability of y given x, and let's separate this, and the probability of x. Two different ways of writing the same joint distribution. What's going on in linear discriminant analysis is we're explicitly modeling these as Gaussian, and this is Bernoulli. It's a completely specified joint distribution, and so it's usually called a generative model. Generative just means you specified a probability distribution, so that if you wanted to generate from this model, you could do it because you know the whole distribution. But in logistic regression, what we're doing is we're estimating this part of the model only. This is logistic. We never actually say anything in logistic regression about what this is. We just we're sort of agnostic about what that is. To find the estimator, we used this conditional part of the likelihood function, and we ignored this. And that's usually called a discriminative model. It goes directly for doing discrimination or classification without trying to create a fully generative model. Yes?
Does that mean that the fit will be independent of the marginal distribution of x?
I'm sorry?
Does that mean that this will be independent, your logistic regression estimator will be independent of the marginal distribution of x?
That's right. We didn't use anything about the marginal of x. Yes?
But does the equivalence mean that the assumption is conclusive?
The equivalence is only in the form of the model. The actual parameter estimates you get out are different from the two. And the question is, which approach gives me better parameter estimates? And the answer is this. There's sort of two answers. If the generative model is correct, then we know from standard theory that the MLE is the optimal estimator, and you would be better off doing this. And this, therefore, leads to an inefficient estimator. The asymptotic relative efficiency, remember we talked about 75, of these parameters would be less than 1. However, generative models require you to specify more of the model. Discriminative models allow you to be agnostic about part of the model and just only specify the part of the model you care about, which is y given x. And so there's a certain robustness here that you don't have to get as much of the model correct. This is the trade-off in general between discriminative models and generative models. Generative models sort of give you more, but you have to model more. Discriminative models sort of give you less, but they have wider validity because you have to model less of the distribution. I don't think in general you could ever say one is always better than the other one. And frankly, it's usually just a matter of convenience which one people use or very problem specific. But you will hear these terms generative versus discriminative, and it's really just a matter of whether you break the distribution down this way and model it this way, or break it down this way and just model this part of it. That's the difference between discriminative and generative models. Okay? But it's true that in some sense, if you do LDA and your friend does logistic regression, in some sense you're kind of fitting the same model, but you're fitting them with two different methods. One of them is using the logistic likelihood, the other one is using the Gaussian approach. So you're not going to get exactly the same estimators, even though you both end up with linear classifiers at the end. So it's not people make a big deal about it, but it's not really that big a deal. I just wanted to mention it because that term gets used a lot, generative versus discriminative. There is a kind of philosophy some people have, which is never model more than you have to. Why put down models for things if you don't have to? So that tends to lead people towards the logistic model because they feel like they're modeling less. Okay, but logistic regression, at any rate, is like linear regression. It's a parametric model. It might work well even if the model's wrong, but it certainly isn't going to work well as we've described it if D is bigger than N, if there's more features than there are data. For the same reason why we couldn't do linear regression if the number of features was larger than the sample size. What we did is we added some sort of sparsity penalty. So you can do exactly the same thing for logistic regression, is we take that log likelihood function for beta, and since usually we talk about maximizing the likelihood, but now to think about it like a loss function, as we were just saying, if we want to think about minimizing, let's put a minus in front. So we're going to minimize the log likelihood, just like minimizing the sums of squares in regression. Now you just add a penalty function. like we did in the lasso. And that gives you a logistic version of the lasso. So there's various algorithms for doing this. It's a convex problem. You could use your favorite convex solver or whatever people use. In statistics, people tend to just do actually coordinate descent, which in principle is often not optimal, but in practice seems to work very, very well. The most commonly used software in R is called GLMNet, not a very good name. But anyway, it does for you sparse, it does the lasso, it does stepwise regression, it does sparse logistic regression. It's doing a coordinate descent, which means it's minimizing this one beta at a time and iterating. In fact, if you're interested in the steps, they're actually in the notes. If you don't care, that's fine. But if you want to know what they are, they've been worked out for you. It's a very simple algorithm. And so implementing sparse logistic regression is quite simple. It's not much harder than doing ordinary logistic regression. And of course, we're going to have to now choose the parameter lambda by some form of cross-validation. We're going to look at some examples in a few minutes.
You mentioned being concave somewhere in the logistic regression.
This is concave, so this is convex. Yeah. So sparse logistic regression is a really, really good high-dimensional classifier to consider as a first option. Very fast, very simple, easy to interpret, and lots of existing software for doing it. So we'll look at an example of that in a minute. I want to mention now one more linear classifier, or a linear version of a classifier, which are support vector machines. Now, when we talk about non-parametric classifiers, we'll talk about the non-parametric version of support vector machines. For those of you who are familiar with support vector machines, you're probably more familiar with the non-parametric version. But I'm just going to start with the linear version since we're doing linear classification. So basically, the simple explanation is, well, first of all, I'm going to recode. This is one of those cases where it's probably helpful to recode. Instead of 1 and 0, I'm going to use +1 and -1. And I can write any linear classifier then as taking the sign of, let's say, h of x, where h of x okay, so this is a linear classifier. By the way, one classifier I didn't mention is the empirical risk minimizer. In principle, you could take any linear classifier, compute the training error, and try to find the hyperplane which minimizes the training error. That's the empirical risk minimizer. That's also a linear classifier. The difficulty with that is that that's not a differentiable, nice, smooth function, right, the training error, because it's 1-0 function. So that's a difficult classifier to find. And so what happens with a support vector machine, or at least one way of viewing the support vector machine, is to use what we can think of as a surrogate loss function. So I'm going to draw that picture. If we look at, let's look at the loss function. When is y not equal to h? That's precisely when, because we're taking the sign of this, right? So that's precisely when y times h of x is negative. Because if these are both positive, you've classified correctly. If these are both negative, then this will be positive and you classified correctly. But if the signs of these differ, that's when you've made a mistake, and that's precisely when this is negative. So if I think of the x-axis as y times h of x, where every time that's negative, we're making a mistake, and every time it's positive, we're classifying correctly. So for linear classification, we can draw this picture, which is just showing again that the usual classification error is a 1-0 function not concave, not differentiable, hard to deal with. So that's why, again, if I try to minimize the training error, if I tried to minimize the sum over all betas, it's very hard to do that computationally because it's not a nice function. So the way I like to view a support vector machine is let's take this clumsy loss function and try to approximate it with something better. I already mentioned, I got ahead of myself there and said that logistic regression you can view, if you look at the minus log likelihood function, it's like replacing that with a smooth function. But you might ask, why don't I choose some sort of function that is, we want to stick to convex functions because those are easier to deal with computationally. But maybe I should try to find the smallest convex function that approximates this. In other words, stay above the loss function, but keep it convex. In some sense, that's the best approximating convex function in some sense, right? And that function is just called the hinge function. So what we're going to do is replace the formula for that function is simply 1 minus y h of x plus. Plus means if this is negative, set it equal to 0. So if you look at this function, that's precisely what this function is. So what we're going to use is we're replacing the 1, 0 loss function with a surrogate loss function, with a replacement loss function that's going to be easier to deal with numerically. We're going to minimize this loss function instead. And so what we end up doing is minimizing this. This is called, again, the hinge function because it looks like a hinge. And we're going to do one more thing. We're going to add in like a ridge penalty, a little bit of normalization.
Why L2 here?
Good question. Why L2? We could do also L1 as well. But to make the connection with the usual support vector machine, we're going to stick to L2. And eventually, when we get to non-parametric, it's because this is going to become a reproducing kernel Hilbert space norm. So it's going to play a kind of non-parametric role. So for now, just think of it as a definition. We're minimizing the hinge loss plus a ridge penalty.
Is there any advantage to like an L1 penalty?
Yeah.
If you're not looking for sparsity?
Oh, no. I think the advantage of the L1 is only for sparsity.
I should always prefer L2 if I don't care about sparsity.
Well, I wouldn't. I'm loath to say you should always do something, but the truth is this is really to connect it with how support vector machines are originally defined, which has a more geometric flavor. I'll say that. I'll make the connection in a second. But for now, all I'm doing is I'm taking the 0, 1 loss function, I've replaced it with a surrogate loss function, and added a bit of a penalty. Yes?
I was wondering, why that particular slope? Can you consider like
There are generalizations of considering other. So there's a whole literature now about surrogate loss functions. And you can consider other slopes, other shapes, and so on. And there's actually quite a literature about, you can see that you gain some computational simplicity, but maybe you're losing something in the generalization. So there's a whole theory about this now. So I just want to introduce sort of the first one, the most basic one. But you're absolutely right. We could consider other surrogate loss functions as well.
What's the advantage of adding a penalty?
Well, because a few advantages, but the main right now it's just to define what people mean by a support vector machine. It's just a matter of definition right now. Because if I minimize this, so this is a convex thing, and so you can fairly quickly find the minimizer. So now you're going to get another. You're going to get this pops out of it, and that's your classifier. So your classifier, this is your H hat, and then your classifier is the sign of this. What I'm trying to get across, though, is that if we define the target to be minimizing this, we get a linear classifier, we have another linear classifier. It's a different one. And the key step, don't worry too much with the regularization, that's going to play a bigger role later. The key step was replacing 0, 1 loss with a convex surrogate loss function. And it leads again to a linear classifier, but it can be solved computationally efficiently. And there's theorems, again, about how much do you lose by replacing the 0, 1 loss by this surrogate loss function. There's a bit of loss, but under certain conditions, not too much, especially if you're lucky and there's not too many observations near here, this is the margin, this area, then you can actually get very good classification doing this. See, I forgot which results I may or may not have included, but we'll see. So this is the definition of the support vector machine. It's usually defined in a different way. People usually do this. They say, let me use dots. I want to use symbols. These are like 1s and -1s. And at first, if you say, suppose that they're perfectly linearly separable, the original motivation was, well, we can then use a linear separator. But what's the best one? Well, you might want to pick the one that's as far as possible from the closest guys. I didn't draw that very well. If you had a choice of perfect linear separators, what you want to do is find these support vectors, the closest vectors to the thing. And you don't want to get too close to either class. Intuitively, it seems like staying in the middle is a good idea. That leads exactly to the hinge function, it turns out. It's just a reformulation. And what the L2 loss is really doing is when you don't have a perfect linear separator, you're going to have to allow some slack. You're going to have to allow some of these to creep over. And that's where that turns out to correspond to. So the original description of a support vector machine is find a good linear separator that kind of really well separates them with a sort of a clean margin, as clean as possible. But it turns out you can mathematically rewrite it in the way I've written it. I find this much easier, personally, to understand, maybe because I'm used to regression and things like that. They're mathematically equivalent. But there is another type of sparsity going on here, which I didn't mention so far, which is that the final classifier really only depends on these support vectors, the ones that are closest to the boundary. It turns out that these other vectors don't affect the classifier very much, or at all, actually. So there's this kind of a sparsity in the sense that, not in terms of the betas, but in terms of which examples are driving the classifier. It's the ones closest to the classifier. The key vectors here are the support vectors. And so there's a different type of sparsity going on in support vector classification.
So the support vector, that includes misclassified points?
Yeah, so when you add slack variables in, as they call it, you allow a certain amount of crossover.
And those influence the...
Yeah, and that turns out to, again, corresponding to exactly this, minimizing this. Yeah, so I don't want to belabor this because the computational connection between this and the original version is, I think, interesting in an optimization class. It's not something we care too much about in this class. What's more important for us statistically is when we do the non-parametric version, this is going to get replaced. This is going to get replaced by an arbitrary function, not just a linear function, but it will live in a reproducing kernel Hilbert space. And this will get replaced by the reproducing kernel Hilbert space norm. So that's a clear explanation of what this is doing here. It's allowing us to make this into a non-parametric classifier. So we'll do that when we do non-parametric classification. And one of the very cool things is if you have code to do a support vector machine, you're going to have inner products of things all over the place. And to change your code just amounts to changing it. Every inner product just gets replaced by the kernel you're going to use for the reproducing kernel Hilbert space. So it's kind of like one little change to your code, and you automatically have gone from a linear support vector machine to a non-parametric support vector machine. So there's a lot of cool things about these support vector machines. Although, for whatever reason, there was a period of time when they were all the rage. That's all anybody talked about. Now they seem to not be people aren't as excited about them anymore. I guess because deep learning maybe is taking over, crowding out the field. I don't know why, but anyway, this is a good way to view it. And again, logistic regression is equivalent really to just using a different function. If you write down minus the log likelihood, you can think of it as a function of this times this. You'll see it's a different function. When we talk about boosting, we'll see that that corresponds to a slightly different surrogate loss function. So these surrogate loss functions pop up either explicitly or implicitly in many different classifiers. All right. Just wanted to go through, before we go to non-parametric classification, I wanted to go through a kind of interesting example here. My former student and colleague, Han Liu, who's at Princeton, did these two examples in some detail. They're actually pretty nice examples, I think, of how far you can get with linear classification. So the first one, here's on page 24. This one comes about because I work with quite a bit with astrophysicists, so I tend to get interested in astrophysics examples. So what you're looking at, these pictures are supernovae. These are exploding stars. Supernovae play a very, very important role in astrophysics because supernovas, when you plot their intensity of their light over time, it looks like this. And this happens in a matter of days. Most things in the universe, we're talking about millions of years, how long things take. This happens in a matter of days. And roughly speaking, every supernova, this is approximately true, has the same peak brightness. So if I look at a supernova and I say, how bright does it look to me, but we know how bright it really should be, I can tell how far away it is by the difference between its apparent brightness and true brightness. So they're called standard candles. So supernovae are very, very important in astronomy because they allow you to calibrate distances. But there's different types of supernova. So the ones that we have here, these are after the supernova. These are the remnants, as they're called. The one on the left, the one on the right is called a supernova type 1a. And the one on the left, I forget which type it is, but there's different types of supernovas. It's very important to tell them apart because for using them for these standard candles, they need to use the right type of supernova. So they need to be able to tell apart type 1a supernovas from other types of supernovas. So we're going to try to treat this as a classification problem. You can have astronomers look at these images, spend a lot of time classifying them, but then when you get telescopes collecting millions and millions of things, it becomes impractical after a while. So it's perfect for having trying to do some sort of automated classification. But I wanted to show you, some of the realistic complications that occur in a real problem. So if you look at page 25, those are 4 curves. These are these light curves I'm talking about. In fact, they're on the same supernova, and what I didn't tell you was that they measure these curves in different colors. So G is green, R is red, I is infrared, Z is, I forget what it is. So one thing is, we have multiple light curves per supernova, but more importantly, we don't actually observe the whole curve, we just observe some points on the curve. To make matters worse, they're measured with error. That's why there's bars around there. So a lot of times you have to think really carefully about how am I going to do classification then? What am I going to do? So a lot of times there's some pre-processing that you're going to have to do to make sense of it. What we did in this case was we used non-parametric regression. So what we did is we took a non-parametric regression and put it through these points. So that's a preliminary step. Why did we do that? Now for every supernova, I have a definite curve. There aren't these gaps between the different things. Okay, and then we extracted features from these curves to do classification. There's actually 2 sets of features which Han called the time domain and the frequency domain. You can ignore the frequency ones. They didn't work. It was worth trying, but and the features are just the heights of the function at a grid of points. That's the features. So now we've converted it into a pretty standard classification problem. Every supernova is either a type 1a or other. And I have a vector of features, which is just these fitted regression functions evaluated at a grid of points. That's the x's. Now I can just feed it through any sort of classifier I want. So what you see here is on the left, you can just focus on the left one, which is the ones we end up using. That's a plot of sparse logistic regression. So whenever you do any of these sparse things like the lasso, remember that what ends up happening is when you have full regularization, all the coefficients are 0. Then some of them become maybe non-zero for a while. This one might become non-zero later, and so on. As we loosen up the regularization, more and more beta hats become non-zero. And that's what you're seeing here, is that the model's going from very sparse to very complex. And on the next page, what we're going to look at is the test and the training error. And we're comparing sparse logistic regression to support vector machines. And if you just look at the top plot here and this one below it, what matters really is there's two sets there, which is the training error and the testing error. What we care about is the testing error, which is the higher curve. And what's interesting, and there's also a regularization parameter in both of them, is how similar they are. In this particular case, they both get down to about, it's so small I can't read it, but maybe about 20% error rates. And at least if we choose the regularization in the right area, we get 20%. And there's not much difference between the support vector machine and the sparse logistic regression in this case. I think this is a good thing to do in general, right? You don't necessarily have to pick one method. You can compare how different methods are doing. And there's some more comparisons with these box plots on the left. And I forget, a good question is, how does our classification error rate compared to what was considered the best at the time? I think this was pretty close, but I've actually forgotten right now. So I'm not sure how, is 20% good or not? I'm not actually sure right now. But at any rate, that's just a good example of classification in practice. A second one is based on, this was an older election. This is good timing for talking about elections, I guess. But this was the 2004 election, so this is quite a while ago. And this is just looking at a bunch of blogs. I think I mentioned this example before. And the features are just word counts. Take a list of words. How often does this word occur? So those are the features, and everything has been classified as conservative or liberal. And once again, we're comparing sparse logistic regression and support vector machine. They turn out again to be very, very similar. There's actually two classifiers, one that only uses the word counts and one that actually uses information about links to other pages as more features. The links seem to help. And an interesting thing is the support vector machine, there's standard errors around these classification errors. So the support vector machine, it seems to be a little bit more variable. But other than that, they seem to be performing very, very similarly. So this is another example where we could use either support vector machines or sparse linear regression. There doesn't seem to be too much difference. And again, we're getting about, by coincidence, maybe a 20% error rate in the classification. For comparison, we also did linear discriminant analysis, which was like 30%. So at least they are outperforming linear discriminant analysis, but sparse logistic and support vector machines seem to be about the same. Okay, so that's just a couple of examples of applying these things. The last thing I want to mention is a little bit of theory. In fact, we've already talked about some theory, and I just want to mention two results. One that we can pull from the concentration of measure stuff that we did earlier, and then I want to show you a different style of result that's possible. We already know from VC theory that linear classifiers, they have a finite VC dimension, and we saw that if we can control using concentration of measure, if I take the soup over all linear classifiers and I look at the training error and the true error, we saw that we could control that, right, by something, I'll leave out constant, something like n to the d, e to the minus, and epsilon squared times. See, that was because I should really have d plus 1 because the VC dimension of linear classifiers in d-dimensional space is d plus 1. And remember we proved that if you have the training error and the classification error uniformly close, that means when you minimize the training error, when you do empirical risk minimization, you're also getting close to the minimum of the true error. So that's why we have this result that in page 31, that if I really did empirical risk minimization, now we're not actually doing pure empirical risk minimization because of the computational problems. But if we did, how much would that differ from the best linear classifier? Well, thanks to VC theory, we know that, I'll put in now the constants. It's 8n to the d plus 1. And so this is an example where VC theory tells us that empirical risk minimization, as n goes to infinity, this is going to go to 0 pretty quickly, as long as the dimension is fixed, or doesn't grow quickly, because then the exponential term will take over. However, you might wonder if there's other ways to bound the error. And I just want to give you an example of how other bounds are obtained using pictures like this. You know, when you draw it this way, you can see that things over here we're not going to have trouble classifying. Things over here we're not going to have trouble. It's the things near the decision boundary that cause the problems. Is there some way to say if there aren't too many data points near the decision boundary that maybe I can get small classification error? Maybe I can improve on this VC bound by taking into account more information. So there's many such results. The one I'm going to quote is from a paper by Kolchinsky and Panchenko. And here's how they do it. There's different ways you can do this. But what they do is they draw a picture like that. So it's going to be slightly different, though. I'm going to take a number, gamma, and I'm going to draw this function. It's not the hinge function anymore. It's a kind of smoothed out version of the 0, 1 loss function. This function here we'll call phi sub gamma. And this is for an arbitrary gamma. Just fix a number gamma. They prove the following result. This is again for linear classification, although there's generalizations to other classifiers. The probability of misclassification is less than or equal to. And now look at this function, phi gamma. So this is like, again, a smooth version of the 0, 1 loss function. It's sort of the price you're paying here, plus I'll leave out constants, something like d gamma over n, and smaller order terms. So what's going on here? What's happening is this is sort of just doing like a weighted count of the misclassifications in here. So think about this. Suppose that there's no points in the space near the decision boundary. That corresponds to saying that there aren't many examples that fall into this region. Then I could take gamma pretty big, and this sum is not going to involve anything. This is going to be 0 or very small. And I can take gamma big. What that's going to do is make this whole error very small because I'm taking gamma big. So it's saying you're doing linear classification and there aren't many data points near the decision boundary, you get small misclassification error. But that would only be true, again, if there weren't many points near the decision boundary. But the point is here is that you can get bounds on the misclassification error that are sensitive to how the data are. Are you in a situation where there's a lot of points near the decision boundary or not? That's missed in the VC theory. The VC theory is a much broader, but on the other hand, more crude way to bound the classification error. Now the proofs would take a long time and would be a few lectures. So if you're interested, that's the reference there. But I wanted to at least give you a feeling for the fact that there are other ways to bound the misclassification error other than using VC theory. There are some restrictions, by the way, I should say, is that the proof assumes everything's bounded, and as far as I can tell, the boundedness assumption here is crucial to making all the proofs work and everything. So there are some, whether it's a better result or not, there's trade-offs here. You're making certain assumptions that you wouldn't necessarily have to make to use the VC bounds. So those are just two examples of theoretical results that are available for linear classifiers, which I wanted to mention since the whole section was about linear classification.
So as you say, there's no points yet about that refers to the true distribution.
No, this is actually in the sample. We're summing over the sample points. This is a sample-sensitive bound. Yeah. And I should say this bound holds with high probability. I should have clarified that. With probability at least 1 minus delta, there's another term involving delta over here. We have this bound. All right. How are we doing? So I think we're ready to move on to non-parametric classifiers. Is there a way to further bound that term? Possibly. I'm not sure. I think it was considered a victory to get something which involved how many points were close to the margin. So that itself was considered kind of revealing.
Well, this bound relates to the sample. In which term they have some.
Here's the points in the sample.
But here we said that H is any classifier.
No, this is a linear classifier. Did I say any classifier?
Did that classifier depend on sample?
Sorry, yeah, you're right. The bound I stated was for any classifier.
Why that classifier should relate it to the sample we have?
Yeah, so this is for any classifier. In practice, you're going to use this for something which is chosen from the data. So this is going to be actually H hat. But since this holds for any classifier, it also holds for the one chosen from the data.
No, but I believe that probability it should be a constant thing regardless of what sample do you have. Because that's just a probability that y is not equal to.
No, that could be random. If H is random, then that will be everything will be a random variable there. That's why it only holds with high probability, the whole thing.
So the choice of H is related to how you choose gamma in.
Well, so in principle, yeah, the hope is that when you're doing this, you're choosing something with a small that. This is sort of supposed to be explaining why you want to choose things that don't have many points near the margin.
So why not just to choose gamma to a very big number when you are just in the classifier?
Because that might make the other term blow up.
There will be a lot of points.
This could be huge. It depends on the data.
You mean the first term?
Yeah, it could be. You could have just ones and zeros. You'd be getting everything wrong, and that could be big. Margins will come up again when we talk about boosting. Shortly, actually. In fact, so if there's no more questions, let's move on to the non-parametric case. So the generalization from parametric to non-parametric is similar to the jump in regression, from linear regression to non-parametric regression. In fact, the simplest way to do non-parametric classification is to do plug-in classification. So we already learned how to do non-parametric regression. So we have, this is some estimate of the mean of y given x, which, since it's binary, is the same as the probability. So we already have instantly for us a whole bunch of nonlinear classifiers because we just use this, we just do the plug-in classifier. Any non-parametric regression estimator automatically can be turned into a non-parametric classifier. And we even had a result, remember, that the resulting, the risk, the prediction risk of this classifier compared to, let's say, the Bayes rule, we saw it was less than or equal to, I'll put this version of it, so what that implies is that if you have a good regression estimator, you also have a good classifier. But as I've said a few times, the reverse is not true. We could have a bad regression estimator and still have a good classifier. So how do you actually do this in practice? Which plug-in classifiers would you use? Let me tie my shoe before I trip over myself here. Of course, we have a lot of choices. And in fact, we can even do plug-in to the density estimator, to the density function, as well as the regression, which is a very common thing to do. Because remember, another way to write the Bayes rule was the following. The Bayes rule, we can write it in terms of the regression function m, but remember we could also write it in terms of the class probabilities. It was 1 or 0, depending on whether P1 of x over P0 of x was bigger than 1 minus pi over pi and 0 otherwise, where this is the density of the x's for the whenever y is equal to 1. This is the density of the x's given that y is equal to 0. And pi is the marginal probability of y or 1, y equals 1. So we can automatically do a plug-in estimator very quickly just by, first of all, estimating pi is easy. And what is this? This is just the density of x given y equals 1. Well, we can just put in your favorite density estimator there. And that gives us a plug-in. Another way to do a plug-in classification. So if you like to use density estimators, you automatically have a way of doing some version of classification. And there's a very, very common way of doing this, which is, let's look at this density estimator. We could try to use a kernel. We could try to use something else. But what if x is high dimensional? Well, going again on the principle that we don't need to estimate the functions very well to classify well, maybe we can just put in a pretty crude estimate of the density. I'm going to do a very crude non-parametric density estimator. And it usually goes under the name of the naive Bayes classifier. Why it's got that name, I don't know. It should be called the independence classifier, because what we're going to do is, by definition, assume that the features are independent. We don't believe that the features are independent. We're going to treat them as if they're independent. Well, if the features are each independent, that means to estimate the joint density, I can just do a bunch of one-dimensional density estimators and multiply them. So this becomes the product over the features of P1, let's call it j, of xj hat. So in other words, I'm taking all the guys where y is equal to 1, and I'm looking at each feature. And separately, for each feature, I do a one-dimensional non-parametric density estimator, and I multiply them together. That's a density estimator. And again, it doesn't have to be accurate in order to necessarily classify well. And you do the same thing for P0, and that's the naive Bayes classifier. It's especially popular when the x's are discrete, in which case this is really just estimating a proportion. An interesting thing to think about is, if I do this, I've now got the distribution of x given y and the distribution of y given x. What if I turned it around and said, what model does that imply for the mean of y given x? If I use this thing, and now I ask myself what the regression function looks like. So here's a good exercise. It'll take you 2 minutes. You're going to get back what we call the additive model. This is like using an additive model for the log probability. So there's a connection between this and what we call additive modeling. You can see, because taking the log of a product is just a sum, right? So it's not too surprising. So this is a surprisingly successful method, because you see people do this, for example, with documents, and they treat words as independent. And we know words aren't independent in documents, but that leads still to very, very good classifiers. So that's another type of plug-in estimator. Let's talk about one that you may have used many times without realizing it's a plug-in estimator, which is k-nearest neighbors. So what's the k-nearest neighbor classifier? This is maybe one of the oldest non-parametric classifiers. And in case you haven't seen it, I'll tell you how it works. Suppose your data look like this. You pick a k. Let's say, just for example, k equals to 3. And I suppose my new point is here, and I want to classify it. You find the 3 nearest neighbors. In that case, it would be 1, 2, 3. And you vote. If there's more 1s than 0s, you make it 1. Your prediction is 1. If there's more 0s than 1s, you predict 0. Is that clear? People usually use odd numbers to avoid having to deal with ties. Very simple. And under very weak conditions, like that if k goes to infinity as n goes to infinity, but is it k over n has to go to 0? Actually, let me check. I forget whether it's k over n or k over n to the d. I'll get to the theoretical results soon, so why should I do it now? Under very weak conditions about how k behaves, you get a consistent classifier. There's ways, finding the nearest neighbors can be expensive, but of course there's a lot of computational methods for doing that quickly. So it's a very simple, popular classifier. But it's really just a plug-in classifier. If you think about it, I could simply do first an estimate. So first of all, when I say they're voting, I'm just saying, is the proportion of 1s here bigger than a half or less than a half? So all I'm really doing is a non-parametric regression where I'm using a kernel, a spherical kernel, but I'm letting the bandwidth change with x. dkx here is just the distance to the kth nearest neighbor. So in other words, I'm just saying, let's find, here's the third nearest neighbor. We go out that distance. And all we're doing is counting. What's the proportion of 1s and 0s? So this is just counting the y's. And the weights are simply, are you in that neighborhood or not? And all we're doing is checking whether m hat of x is bigger than a half or less than a half. So a k-nearest neighbor classifier is exactly a plug-in classifier using a k-nearest neighbor kernel regression. Even though it's not usually thought of that way, that's exactly what it's doing.
Like your kernel exists in the k-nearest.
Yeah, so one thing, when I did kernel regression, I didn't mention this. We always did fixed bandwidth regression. But you could take the size of the kernel to be the distance to the kth nearest neighbor. That's called k-nearest neighbor regression. And that's a more kind of an adaptive choice of the bandwidth. And that's precisely what KNN classification is doing. So often you can take familiar classifiers and rewrite them this way as plug-in classifiers, which is not that necessarily makes it more useful or anything like that, but it just helps to provide a kind of unifying framework for thinking about these classifiers. All right. So there's lots of results about K and N classifiers. I wanted to mention two. I'm at the bottom of page 4. This theorem is due to DeVroy and Gyorfi. We're going to assume only that as n gets bigger, you choose more and more nearest neighbors, but not too fast. This is what I started to write a moment ago, that k does not grow as fast as n. And then the following is true. The probability that the k nearest neighbor classifier misclassifies compared to the Bayes classifier, the probability that that's bigger than epsilon is less than or equal to e to the minus n epsilon squared over 72. And there's this constant gamma, which is just something which comes up in the proof. It's a constant, but it's not quite a constant because it actually does depend on the dimension. So this is only a fixed dimension result. If the dimension was changing, this would kind of screw things up. But for fixed dimension, you can just think about this as a constant. So what this is saying is for a fairly wide range of choices of k, you get good classification rates from using a k and n classifier. Of course, in practice, you're not going to use an arbitrary k. You're going to use cross-validation, presumably, to choose a good choice of k.
What is H star?
That's the Bayes rule. That's the best classifier. We can compare it to the Bayes rule because it's a non-parametric method. OK, but now I wanted to show you a different style of result. Until we get to minimax theory, I'm probably not going to be going over any proofs anymore, or we'd spend the whole course just going through proofs. So right now I just want to give you the results so you get some qualitative understanding of how these things behave. We'll start doing a few more proofs when we get to minimax theory. But this is an interesting result. This is a very recent result by Chaudhuri and Dasgupta. This is only a year and a half old or something like that. Well, I wanted to mention it just because it's a different style of result, and it takes into account something that we're going to talk about later. It's again about roughly this margin behavior. So this keeps coming up for us, right? That let me draw, again, a regression function. Here's an arbitrary regression function. We know all we're really checking is whether you're above half or less than half. And the reason why you can classify well, even with a poor regression estimator, is all you have to do is get on the correct side of this. One way of capturing this, and this was initially due to work by Sasha Sibikov, so sometimes people call this the Sibikov condition, but it's a type of margin condition, which is the following thing. You could imagine, let's imagine actually some different scenarios. Suppose the regression function looks like this. If I get a data point that falls around here, I'm going to have difficulty. Imagine it's sort of bobbling around there. I'm going to have difficulty classifying that correctly, right? That's a tough problem. But this one looks easier, right? If I get a point here, I'm safe. If I get a point here, I'm safe. Even here, unless I'm really close, I'm safe. In fact, let's look at I haven't said anything yet about the marginal distribution of x, but that plays a role too. Suppose the marginal distribution of x was all of the mass was here, very low here, and very high here. This danger area wouldn't matter because I don't have a high probability of being in the danger area. So what really matters is what's the probability that you're close to the decision boundary. And so one way of capturing that is suppose that the probability, imagine drawing a random x, and asking yourself, what's the probability that the regression function evaluated at x compared to a half, what's the probability that that's less than t? And let's suppose that's less than c times t to the beta. This beta is telling you how difficult the problem is. if there was no mass near the boundary, then when t is small, this has to be 0. Beta is going to be huge. An easy problem corresponds to beta being large, right? That would make the probability in a small interval around here. If beta is huge, small number to a huge power goes to 0. So an easy problem, a problem where you don't tend to get points really close to the decision boundary, has a large beta. This is a way of characterizing for a particular distribution, in some sense, how difficult is the classification problem for this particular distribution. It's a distribution-dependent quantity. Okay? And sometimes this is called the Sibikov noise exponent. So what they proved was that if you do k and n classification, and they're also going to assume a kind of a Lipschitz condition. It looks a bit odd if you look at it, but just think of it as our usual Lipschitz condition on the regression function. It's actually slightly different, but it doesn't matter. Some sort of smoothness condition on M, which is going to be represented by alpha. So I used beta a lot before. I'm using alpha now. And if you take k to be, this should look familiar, right? Think of this again as the smoothness. The alpha is measuring the smoothness of the regression function. But here's the cool thing, is the k and n nearest neighbor classifier with this choice, if I take into account this behavior, let's look at what the classification risk is. It's alpha beta plus 1 over 2 alpha plus 1. And in particular, what happens when beta is large? So suppose we have an easy problem, large margin, if you want to think of it that way, not much data near the boundary. Beta is getting big. You can see this is going to 0 very quickly. So what this is showing, and this is for k and n classifiers, but there are similar results for other classifiers, which is that if you have what's called either a good margin or low noise, some people call it, you get fast classification rates, which wouldn't happen in this. There's no such results for regression. This is because classification has a sharp boundary. And if you don't have a lot of probability mass near a sharp boundary, classification becomes easier. So I wanted to give you this style of result too, because it's different than this is a more traditional result.
Is this the true regression function?
Yeah, this is referring, that's right. So this is saying if your true regression function satisfies this condition, then a k and n classifier will have very low misclassification error. Now this assumes you're choosing k this way, but that doesn't matter because we know we can choose k from cross-validation and do a very good job of finding a good classifier. So you'll come close to choosing a good k. And so it's only for theory that we need to specify the specific value of k. So this is similar to the other result I showed you again, where there's some sort of notion that if there's not much probability near the margins, you can do well in classification. So I wanted to give those two results because this is a more traditional one, and this is more margin-oriented. Okay. How are we doing? A couple more minutes. All right. Let's talk about a few more non-parametric classifiers. We can just start this. One of the most successful classifiers right now, as I understand it, is random forests. How many of you have heard of random forests? Almost everybody. And I don't think anybody knows why they work. There's intuitions about why they work, but let's just back up and talk about that, we have to remind ourselves how the trees work. We did trees for regression. So a classification tree is just like a regression tree where we choose a place to split. Ideally, you would split by, you would measure, this is now going to be, think of this as a classifier which is going to classify according to whether the majority are 1 or 0 here, and similarly over here. And we would try to choose the split with the lowest misclassification error rate. That's non-differentiable, so people usually use a surrogate loss function again. They use some sort of smooth function that can be optimized quickly instead of misclassification rate. And then they recursively split. So now maybe we'll split here, just like we did for the regression example. And as before, you get out a tree, and it has all the nice advantages that a regression tree had. It's kind of simple, pretty easy to interpret. There's some pretty fast algorithms for building these trees. And at the end, we have a classifier where down here, you're going to count how many guys in this cell. It's another plug-in classifier, because all you're going to do is look at how many 1s and 0s there are. And if it's bigger than a half, you're going to classify as 1. But if it was less than or equal to a half, you would classify as 0, and so on. It's really just doing piecewise linear regression and doing a plug-in estimator. So it's very linked to regression, actually. But we're using it here as a classifier. So I'm assuming you're all familiar with a classification tree. And as usual, you would build the tree quite far and then use cross validation to decide how deep to make the tree. But what we want to talk about are the improvements to trees. Where is that? I've lost my place in my notes. Anyway, I'll just tell you about it. So the two big improvements that seem to work really well are bagging and random forests. Random forests are sort of a bagging with an extra trick. So bagging, so how many know what bagging is? If you know what a random forest is, you should know what bagging is. That's weird. Fewer of you know what bagging is than random forests, but you have to do bagging to do random forests. Anyway. Oh, you at least heard of. Okay, fair enough. So let me explain bagging first. And the nice thing about bagging is I'm going to show you a very cool thing. I'm going to show you a very, very simple theoretical result that explains why bagging works. Okay, the rest of random forests, I don't have a good explanation of why they work so well, although there's some intuition about it. But for bagging, there's a very precise theoretical result that explains what bagging is doing and why it works. It's very cute. And I'll show you the proof, because in a special case, the proof is only about 4 or 5 lines long. And it uses stuff we've learned from 705. So it ties things together very nicely. It's going to use some central limit theorem stuff. But what is bagging? So here's the idea. Is you take x1 to xn, and you get your classification tree, let's say. And all bagging is this. Remember the bootstrap we did in 705? We're going to use the bootstrap. But we're not going to use it the same way. We're not using it to get a confidence interval standard error. We're using it to create an ensemble of classifiers. So what you do is you draw a bootstrap sample. Remember how to do that. You can think of it as drawing endpoints, IID from the empirical distribution, or draw endpoints with replacement from the data. And the y's too. And you get a classifier. Let's call it h hat 1. Okay. I think I jumped ahead a bit in notes. I did things out of order. I've somehow gotten all my notes. Anyway, I'll just do it out of my head. Always dangerous. Now you do this many times and you aggregate it. So we're going to take an average of these trees and then classify according to whether it's bigger than a half or less than a half. So we'll call this h hat of x is 1 over however many bootstrap samples you do. Okay, so you just bootstrap the data, get a new tree, and you can do this to any classifier. It doesn't have to be trees, but it was first done in trees. You get a new classifier every time, then you average them. It's called bootstrap aggregation, bagging. So before we even get to random forest, what I want to show you in Thursday's class is why does this improve a tree? And what we're going to see is what bagging does is it's a variance reduction technique. It essentially leaves the bias of the classifier unchanged but reduces the variance. And we'll prove that in a special case where you can see very clearly what's going on. And then the next step is the extra layer that gets added on for random forests. So we'll do that proof on Thursday, and I'll re-explain this because I did it kind of quickly. Any questions? All right, so I'll see you on Thursday.